Morning, everyone. So I'm going to start out by talking about technology, different burner types, radiant tubes. Then we will touch a bit on economics as it relates to fuel costs and savings. And then we'll talk about environmental issues, green gas emissions, etc. So here we have a chart that shows combustion efficiency as a function of exhaust gas temperature. So in the case of a direct fired burner, this is the temperature inside the furnace before it reaches any heat exchanger. In the case of a radiant tube system, this represents the temperature inside the radiant tube, which is always hotter because heat flows from hot to cold, right? So this curve on the bottom here, labeled epsilon equals 0, represents a cold air burner. So no combustion air preheat. So if we choose a reference temperature, such as 1,000 Celsius or about 1830 Fahrenheit, you will see that the best possible efficiency for a cold air burner is around 50%. And that's assuming that everything's in good working order and properly tuned, which is sometimes not the case with a lot of the older technology that we see out there, right? So moving up the ladder to the next curve, 0.4, this represents a burner equipped with a plug-in recuperator or a centralized heat exchanger. So a big box remotely located from the furnace with tubes and fins, for heat recovery. So with this type of system, we're typically seeing combustion air preheats in the range of 40%. So the aspect ratio of this slide is off a little bit, but typically that results in efficiencies in the 60 to 65% range. Okay. Moving up a step further, the line labeled 0.6 represents what we call a self-recuperative burner, which I'll talk about in more detail momentarily. A more efficient method of combustion air preheating, now we're seeing preheats in the 60 to 65% range. So that means at 1,000 Celsius, we're looking at efficiencies of 70 to 75%. The last step, which represents the best case scenario, would be a regenerative burner, an even more efficient method of combustion air preheating, which results in preheats in the 80 to 85% range. So at our same reference temperature of 1,000 Celsius, efficiencies are now approaching 90%. Okay, so here we have a grid laying out the various burner types and their pros and cons. So first we have the cold air burner. It's generally a very simple device, right? Gas and air come in, mix in the combustion chamber, flame forms, done. No combustion air preheat. So efficiency is low because of that. NOx emissions are generally low as well because you're not preheating the combustion air, so you're not doing anything to raise the temperature of the flame above a normal level. And NOx emissions are proportional to peak flame temperatures. So lower flame temp means lower NOx. The initial cost of this equipment is generally low because it's simple technology, right? But the operating cost is high due to the low efficiency. So now we look at a burner equipped with a plug-in recuperator. So this type of burner would typically be installed in a U or a W-shaped tube. So the burner fires into one leg of the tube, and then the exhaust products travel out through the opposite leg. Exhaust products travel over the outside surface of this heat exchanger. They transfer their heat through the wall to combustion air, which is flowing over the inside surface that preheats the air to, as I said, around 40% of the process temperature, typically. And results in improved efficiency, still relatively low compared to the modern alternatives. NOx emissions do start to creep up a bit due to that combustion air preheat. The cost of this system is higher than the cold air. Of course, you have the added heat exchanger, but it's still relatively low. Operating cost is still somewhat high because you've boosted efficiency somewhat, but not significantly. Next, we look at the self-recuperative burner. So with this type of equipment, the heat exchanger is an integral part of the burner, and it sits directly inside the wall of the furnace. This helps to minimize heat losses to the surroundings, so that improves the efficiency further. So hot exhaust gases travel over the outside of the heat exchanger as they exit the furnace. Cold air flows over the inside surface, absorbs that heat, makes its way to the combustion chamber, and mixes with the fuel, forming a high velocity flame. And these burners are typically pulse fired, so on-off control, or in some cases high-low. Next, we have a special type of self-recuperative burner known as gap flow. So instead of having one large heat exchanger, which you do have out in front in this case, you also have many tiny tubes in the back end, which serve as a secondary heat exchanger. That increases the surface area for heat transfer by about threefold. So improves the efficiency significantly, close to that of a regenerative burner. Combustion air preheats with this type of equipment are on the order of probably says 70 to 80%, and efficiencies at 1,000 Celsius are in the low 80s. So very high efficiency, low NOx emissions, because like the self-recuperative burner, there is some special combustion technology available to counteract the effects of high combustion air preheat. I will describe that in more detail shortly. Initial investment cost is high because it's a complex piece of equipment, but the operating costs are very low due to that high efficiency. Last, we look at the self-regenerative burner. Traditional regenerative burners operate in pairs. One burner fires while the other exhausts, and the exhaust products travel through a bed of ceramic media, usually ceramic balls, and they absorb the heat from the exhaust. And then when it's this burner's turn to fire, the cold combustion air passes through that bed of media and absorbs the heat out of it. So instead of transferring heat through a wall, as with the recuperative system, you're doing it via direct contact with a media, which is a more efficient method of heat transfer. So that results in higher combustion air preheat temperatures. So the cold air from the opposing burner passes through that bed, absorbs the heat, and fires, and its exhaust products travel through the bed of the opposite burner. That's traditionally how regenerative burners work. With the self-regenerative burner, you no longer need a pair functioning in tandem. Each burner is its own compact unit. It contains 6 passageways. Each passageway contains a row of ceramic honeycomb discs, which serve as your heat storage medium. So at any point in time, 3 of these chambers are bringing in cold air for combustion, and the other 3 are exhausting. And then every 10 seconds, pneumatic switching valves on the burner head cycle, and it reverses the flow path. So the chambers which were exhausting are now pulling in cold air and absorbing the heat out of that medium, and vice versa. So the efficiency of the system is very high, of course, but emissions are still low due to that special combustion technology, which I alluded to. Investment cost is high due to the complexity, but operating cost is very low. So now we'll look at some different radiant tube types. We'll start with traditional non-recirculating radiant tubes. That means the burner fires into one end and exhausts out the other. So this type is known as a W tube due to its shape, right? This one happens to be equipped with a plug-in heat exchanger for heat recovery. So this type of system could also work in a U-shaped tube. You know. The burners installed in these tubes typically have a long, lazy flame, which is stretched out over the length of this first leg. The flame usually tends to impinge right about here at that first bend, which can create problems with uniformity, hot spots, etc. Now here's an example of a modern recirculating type radiant tube known as the P tube. This one's equipped with a self-recuperative burner. As I said, high velocity flame, pulse fired, individual valve control on each burner. So unlike a proportionally controlled system, if one burner goes out, it doesn't affect any of the others in the zone. So this burner fires into the upper leg, exhaust products travel back through the return leg, up through the cross connection, and then the high velocity jet creates a Venturi effect to re-entrain a portion of the exhaust gases back into the upper leg. The geometry of the tube and the flow rates are designed such that you get about 3 recirculating passes inside the tube before exhaust products finally travel back over the heat exchanger, transferring their heat to the incoming combustion air and out the exhaust. Here we have an example of a double P tube, so 2 return legs instead of 1. The burner fires into the center leg and recirculates on either side. And this happens to be a self-regenerative burner installed in this case. This is a common package used in vertical strip lines for the steel industry, galvanizing, inline annealing, other processes such as that. Here we have a single-ended ceramic radiant tube. This material is reaction-bonded silicon carbide, or SiC. It has twice the heat flux capacity of an alloy, so that means it can withstand 110 BTU per hour for every square inch of surface area, as opposed to about 55 to 60 for an alloy tube. This material does not sag, creep, or distort. You never have to rotate the tubes to counteract sagging. You do not have to support the end. Not only do you not have to support the end, we insist that you not try, because your furnace refractory will expand and contract at a different rate than the silicon carbide, and it could lead to cracking. So the tube is simply cantilevered inside the furnace, like you see there. Our largest ceramic radiant tube is 7.7 inches diameter, 110 inches long, and it cantilevers, like you see there, without any problems. With a single-ended radiant tube, whether it be alloy or ceramic, you need these inner tube segments to define the flow path for recirculation. So the burner fires into the tube, exhaust products travel down the inner tube assembly, they reach the end, and they flow back in this annulus between inner and outer tube. And then they reach this all-important gap at the tip of the burner, small gap between the recuperator and the first inner tube segment. And once again, the high-velocity jet from the flame creates a Venturi effect to entrain a portion of the gases back into the inner tube, where they are recirculated several times. So this recirculating technology leads to much better temperature uniformity, which means better product quality, longer tube life, especially in the case of an alloy radiant tube, because they do not like significant temperature differences. And it also leads to lower NOx emissions, because when you mix everything thoroughly inside a tube, it brings down temperature peaks, and this helps to lower NOx, which we'll touch on more in a moment. This graph represents some experimentation conducted in our laboratory in Germany. They tested various tube types, non-recirculating versus recirculating. They placed thermocouples on each leg of each tube, approximately 6 inches apart, and they were looking for the maximum temperature gradient. Where did it occur, and how large was it? So in the case of the W tube, the maximum delta T was observed in the first leg, which makes sense because we have that long, lazy flame there stretched out across the length of that leg. So maximum delta T was approximately 270 degrees Fahrenheit. Next, they tested a U tube, and they saw a slight improvement, but still well over 200 degrees. With the P-type tubes, they saw a significant reduction in delta T, approximately down to 90 degrees Fahrenheit. And that's due to the internal recirculation inside these radiant tubes. Finally, they tested the single-ended tube, and that yielded the best results by far, and that's due to the fact that the recirculation mechanism is compressed into a single leg. Okay, so traditionally there has been a trade-off between efficiency and NOx emissions, because in order to achieve high efficiency, as we discussed, it's necessary to preheat the combustion air to high temperatures. This leads to high peak flame temperatures, and thermal NOx, which is the primary form of NOx generated in a combustion reaction, is an exponential function of peak flame temperature. So as combustion air preheat goes up, flame temp goes up, NOx starts to take off through the roof. So there are a number of techniques. Many of them have been around for several decades to help combat this. Some are fuel and air staging. That's really the same idea, but you're just playing with a different leg of the fire triangle, fuel versus air. So in the case of air staging, which we use in many of our burners, you bring in a portion of the air, mix it with all of the fuel, generate a partial reaction, which is substoichiometric at that point, and release some heat. And then you bring in the secondary air a little further downstream to complete the reaction and release some more heat. So you're spreading the heat out instead of concentrating it at one point. This helps to reduce the peak flame temperatures and thereby lowers NOx emissions. Another useful technique is high velocity combustion itself. The high velocity from the flame creates a lot of stirring and mixing action inside the furnace or the radiant tube. So just as if you would stir a pot of soup on the stove, you're evening out that temperature distribution, right? So you're eliminating those peaks, and that helps to reduce NOx. Flue gas recirculation is also helpful. Exhaust gases are very hot, but they're not as hot as a flame. So by pulling a portion of that exhaust back into the flame envelope, it cools the whole reaction down a bit. In addition to that, the flue gases temporarily disguise, if you will, the oxygen molecules. So it slows the reaction down a bit, which also helps to reduce the peak temperatures. Okay, so as I said, these techniques have been around for quite a while. They're fairly effective, but today NOx emissions requirements are more stringent than ever. Plus, new burner technology with higher combustion air preheat make it more of a challenge to keep NOx under control. Fortunately, there is another technology. I'm not going to call it a new technology. It's been around for a number of years, but it is revolutionary because it brings NOx down to just extremely low numbers, and that is known as flameless combustion. So it's a special combustion technology which occurs above auto ignition temperature, which is generally around 1400 degrees for natural gas. But with this technology, you need an added layer of safety. So you typically switch into flameless combustion at around 1550 Fahrenheit. Okay, so each burner is equipped with two parallel gas trains. One is operating up to 1550 Fahrenheit. The burner is producing a conventional flame at that point. When you reach the transition temperature, that gas train closes, the other one opens. Gas now flows through another pipe inside the burner. Instead of flowing axially out of the burner nozzle, or radially rather, it's injected axially into the radiant tube or the furnace. So the reaction actually starts a bit downstream of the burner. And that fuel is mixed with the combustion air and the recirculated exhaust gases, and a spontaneous reaction occurs which produces no visible flame. So by eliminating the flame from the combustion reaction, as you can imagine, the peak temperatures drop dramatically, and that suppresses NOx emissions to just a fraction of what you could achieve with these conventional techniques. So drastic NOx reduction is the primary benefit of flameless combustion, but a couple other things happen as well. Since you're eliminating that hot spot at the tip of the burner, thermal stress is reduced, and that means critical components such as nozzles, electrodes, etc. are going to last a bit longer. And then while the temperature uniformity of this burner type is already excellent due to the high velocity combustion, flue gas recirculation, etc., it's going to get just a little bit better due to the elimination of that hot spot. Okay, so we've been hearing a lot about green energy lately, right? It's coming our way soon, whether we like it or not, so we need to prepare for that. This chart shows specific CO2 emissions, so normalized, projected over time. So the red curve represents electricity, the blue represents natural gas, the green would be green fuels such as hydrogen, ammonia, etc. So what does this graph tell us? It tells us that we're going to approach the physical limits for combustion efficiency in the next 10 to 15 years. So burners will be as efficient as they can get by that time. So after that, the only way to reduce CO2 emissions further with chemical energy will be by the movement to green fuels, such as hydrogen and ammonia. Electricity will also become greener over time. So somewhere way out here, you'll probably see similar emissions resulting from either chemical or electrical energy. Nobody really knows which one will be the dominant form in the future. We personally think it will be a mixture. I can't see airplanes operating on electricity. May be wrong, but that's just my opinion. Chemical energy is much easier to store in abundance and tap into on demand, right? So we think there'll be a mixture. No one knows what the distribution will be, what the markets will look like, but we need to be prepared, right? So as manufacturers, that's what we're focusing our efforts on today. So many applications, especially continuous applications, can't rely on green electricity alone due to fluctuations in its generation, other issues. Remember the ice storm in Texas a year or two ago where all the windmills froze up, you know? So definitely some issues to overcome, you know? And converting these applications would lead to higher emissions until green electricity is available on a large scale, all right? If green energy is imported from other countries, it's going to be in the form of chemical energy. So to convert that back to electricity before use is not very efficient, right? So it makes sense to just use the chemical energy in the form that you receive it. If designed and engineered properly, today's burners will be able to handle anything from 0 to 100% hydrogen. Okay, and due to the long lifetime of combustion equipment, we're talking like 20, 30-year investment typically, it's necessary to already think about green gas today. So you need to talk to your manufacturer early in the process so they can provide recommendations, because you don't want to install a system today and then have to replace it in 5 or 10 years because now you need to operate on hydrogen. Not all systems are going to be capable of that. The U-tube, for example, so we said it's designed to operate with a long, lazy flame. Hydrogen burns with a very short, hot, intense flame. So you're going to shift the temperature profile inside that tube to a place it wasn't intended to be. So from the first bend there back to the burner tip, basically. And that can lead to overheating, failure, other uniformity issues. Not to mention, hydrogen burns a lot hotter than natural gas. So typically that would lead to even higher NOx emissions. But if you have the right combustion technologies such as high velocity combustion, flue gas recirculation, flameless combustion, you can counteract those effects. Plus, traditional tube types tend to be smaller diameter, longer length, versus recirculating type tubes, which tend to have a larger diameter, which will be helpful with fuels like hydrogen, because larger diameter means more tube surface area, which means lower heat flux across the radiant tube, which ultimately means lower operating temperatures inside, which help to reduce NOx emissions. So there's a lot to think about before you install a new system, because there could be a lot of changes coming in the near future, and you don't want to have to totally replace that system in, like I say, 10 years or so. Here we have an example of a fuel flexible burner. So this could run on natural gas, biomethane, synthetic gas, could run on hydrogen, ammonia, what have you. If you reach a point in time where electricity becomes less expensive than hydrogen, you could use electricity to make your own hydrogen via electrolysis and operate the burner off of that. So if you have a properly designed system with the right flexibility, then you can take advantage of the prevailing market conditions and use the energy source that's most cost effective for you. Here we have a couple of burner system comparisons. This is a forging furnace operating at 2350 Fahrenheit. The net heat requirement to the load is approximately 15 million BTU per hour. So with the cold air system, the gross input required is approximately 42 million. With a central recuperative system, you're able to reduce that to about 33 million. With self-recuperative, it drops to 23 million. And with regenerative or self-regenerative, you're looking at around 20 million BTU per hour. So how does this affect your bottom line? Assuming an annual operating cycle of about 7,000 hours per year, an average load factor of 70%, that means the burners are on 70% of the time on average. And a fuel cost of $8 per million BTU, which is pretty typical at the moment, unfortunately. The worst case scenario with the cold air burner, your annual fuel cost is about 1.65 million. With the self-recuperative, it drops to around 900,000. With the regenerative, you're down to around 785,000. Now we have an example of an even larger system, a vertical strip line, which contains about 200 burners. Strip target temperature is around 1470 Fahrenheit. The net heat requirement to the load is 500,000 BTU per ton. So with the cold air system, you need an input of 1.4 million per ton. With the plug-in, it drops to 1 million. Self-recuperative is 0.85, and regenerative is all the way down to 0.7. So you literally cut your heat requirement in half. So if you want to run 500,000 tons of strip per year, fuel price of $8 again, with a cold air system, you're going to spend more than $5.6 million on fuel. With self-recuperative, you can cut that to 3.4, and with regenerative, it drops to less than 2.8 million. So once again, 50% or more on the savings. So yeah, the savings can be huge. They often amount to 10 to 15 times the additional cost of the investment over the life of the equipment. So to sum it up, there are a variety of burner and tube technologies available, varying levels of complexity, efficiency, cost. Combustion air preheat is still the most effective way to improve combustion efficiency. Flameless combustion enables low NOx with high efficiency, so we can have the best of both worlds. We will approach the physical limits for combustion efficiency within the next 10 to 15 years, and after that, further reduction in CO2 emissions will only be possible by the movement to green fuels. Okay? Due to the long lifetime of combustion equipment, it's necessary to plan ahead today for green gas capability. Green fuels are expected to be more expensive than traditional natural gas, etc. Therefore, combustion efficiency will become even more important in the future. The investment in high-efficiency burners makes sense economically, as we demonstrated through those examples, and the lifetime savings are very significant, often more than 10 times the additional investment. Are there any questions? Yes, sir. The question was, can the ceramic radiant tubes be used in a salt solution? Generally not, at least not reaction bonded silicon carbide. There are some other types of ceramics out there which may be suitable, such as nitron bonded silicon carbide. That falls out of our product range, so I don't have specific knowledge about that, but yeah, could be something to look into. The advantages of the ceramic are, of course, the high heat flux, high temperature capability. These tubes can operate at temperatures up to 2250 Fahrenheit, whereas alloys are limited to about 1850, But they're mechanically fragile, right? They can withstand a high static load, like approximately 2,000 psi, but they can't take an impact or anything like that. And certain atmosphere solutions would be detrimental to the tube, caustics or things like that. Certain special atmospheres can cause an adverse reaction. But of course, there are certain compounds that metallic tubes don't like either, right? So you just need to look at the specific application and decide what the best overall fit is. Anything else? Yes, sir.
You know if the uniformity testing was done with or without atmosphere agitation?
Do I know if the uniformity testing was done with or without atmosphere agitation? It was done in a small test furnace in our lab in Renningen, Germany. I am not positive if a recirculation fan is inside that furnace. My boss is shaking his head no. So, of course, at the temperatures we were testing, around 1,000 Celsius or 1,800 Fahrenheit, radiation is the primary mode of heat transfer, so the fan wouldn't really have much effect at those temperatures. So, all right, one more. We're done? Okay, well, I'll tell you what, I'm at booth 218, so please come and visit me later, and I'll be happy to answer any additional questions. Thank you.